Hello, welcome back. I will start this lecture by basically commenting on problem 6 in the homework because from the solutions that I have seen, only one student got it right for the real part, and no one actually did it right for the complex part. I mean, this is like essential to digital communications. We have two hypotheses, basically, and the likelihood function of the observations has the same covariance matrix under both hypotheses, which is good. But of course, they need to differ somehow, and so they will differ in the mean. Okay, so here the observations under H0. So those are normal with mean mu0 and covariance matrix R. But here, given H1, they are basically normal again, or Gaussian, but the mean is mu1, but the same covariance. And this same covariance will play a role, as we will see later. If the covariance is different, things become complicated. So to minimize the average probability of error when you do a decision, right, because you may make an error, it may be that the true hypothesis is H0 and you decide H1, or it may be H1 and you decide H0. So to minimize the average probability of error, that's a classical proof, then you need to use the maximum a posteriori rule. Which tells you that, go compute the posterior probability of H1, which is the conditional probability of H1 given the vector of observations, and compare it, with the posterior probability of H0 given the observations. And basically, you can write down use Bayes. Okay, so use Bayes, and you can write down the posterior probability in terms of the likelihood function, the prior probability, and you divide here by f of x, assuming that it is not 0, then you can eliminate f of x from both sides, and now you have the prior probabilities are living here. Well, if our hypotheses are equiprobable, then basically this is 0.5 and this is 0.5, and these two terms will go together. MAB rule in the case of equiprobable hypothesis will become the ML rule, the maximum likelihood, because we just need to compare the likelihood functions. So of course, if the priors are not different, so if the priors are not equal, then basically you will need to take them into account if you are doing, your aim is to minimize the average probability of error. Perhaps those guys are different, but anyways, you go for the ML rule by comparing the likelihoods, but your performance will be suboptimal. Okay, so these are basically the likelihood functions. Okay, so they are Gaussian with respective means. So the first thing to say here is that this is the real valued case. So what about the circularly symmetric complex valued case? We basically have 1 over, so the scaling factor outside is different. It is pi to the n, not pi to the n over 2. There is no 2 and it's pi to the n, and then there is no square root, so it's the determinant of r, and then there is no half here, and so it is minus x minus mu1 Hermitian r minus 1 x minus mu1. Okay, so basically this is for if x, so this is x given h1, and it is here circularly symmetric Gaussian, and the mean is mu1, and the covariance matrix is R. Okay, so here the likelihood function is a bit different, but the differences are sort of superficial, and in many cases we'll get sort of the same results. I will comment on another difference when we'll go further steps. Okay, so you write down the likelihood given H1, the likelihood given H0, which again share the same covariance, but they have different mean vectors. Those guys can be eliminated, and you can see basically having the same covariance matrix is very nice, because it allows you, like if here is R1 and here is R0, then these two guys will not go. But now you can eliminate those guys because the under both hypotheses the covariances are. Then you basically take the logarithm of both sides. The logarithm is monotonically increasing, and so it preserves the inequality. And then you get this thing, you multiply by -2, and when you multiply by a negative number, you reverse the inequalities. And then, and this is very important, you expand. Okay, so basically the philosophy is that if you have a hypothesis testing problem, you need to write it down. Your decision rule must be in the most simple form possible. Okay, of course, like in theory, we can just compute these things and compare them. In other words, if we know mu0, mu1, and r, if we get a vector x, we just plug in here and plug in there and compare. But in practice, I mean, these are computations that will be basically implemented on, let's say, a digital signal processor. And hence, what we need to do is basically to reduce the computations by making this thing in the simplest form. Why should I basically multiply by this factor, which is common to both sides? Just eliminate it. Why do I need to exponentiate? I mean, we can just deal with those quadratic forms. But those quadratic forms can also be simplified. Expand. Okay, so when you expand, you get 4 terms. So basically, this is x transpose minus mu1 transpose. So this is the first term. And this will be r inverse x minus r inverse mu1. And then you have 4 terms. You have x transpose r inverse x. And then you have these two guys will give you plus mu1 transpose r inverse mu1. And then you have cross terms. In the real valued case, the cross terms are the same, right? So you have x transpose r inverse mu1 with a minus sign, and then you have minus mu1 transpose r inverse x. And both are the same because in the real valued case, the inner product of A and B, so you can write it as A transpose B, or you can write it as B transpose A. So this is for the real valued case, and so we can have it here. But this is not true in the complex case. In the complex case, A Hermitian B is not B Hermitian A. They are the complex conjugate of one another. Okay, so A Hermitian B, Hermitian, which is because this is a scalar, these are two column vectors, A Hermitian B conjugate, and so this will be B Hermitian A. Okay, so in the complex case, you don't get this term. You get two terms that are the complex conjugate of one another. Okay. Now, here is a simplification. Again, another benefit of having the same covariance matrix, which actually will be the situation in this course, is that you can eliminate the quadratic terms. So those are basically functions. They depend on the squares of the observations, or basically they depend on the product of one observation by another by some constant. But the nice thing, if you have R as the same R in both hypotheses, the quadratic terms here will go away, and so you are left with a linear function of the observation, and this is crucial. Okay, and so, but what basically you have is that you can move basically those to the other side, and this is your basically decision, statistic. So this thing has a name. It's called the decision statistic or test statistic, and so it's the thing that you will compare with the threshold. Here it's a 0 because we moved everything to the other side. Okay, and so basically when you get your vector of observations, assuming that those parameters are known, mu0, mu1, and r, then you get your vector of observation, you plug in here. And this is, relatively speaking, it's simple to compute because, basically this is a known vector. And so basically this thing here is the summation of the components of vector x. And if this thing, we call it basically beta transpose, then we multiply xi beta I and sum over the components. And those will be constants that you can basically pre-compute and store. Okay, so this is the first thing. If you have a hypothesis testing problem or a detection problem, okay, you need to basically simplify it. You know, we all know the MAP rule, we all know the ML rule, which means that you compare likelihoods or you compare posterior probabilities. Everyone knows this. But given your problem, and if you know the statistics, if you know the distributions, you must start from there and simplify as possible. Okay? So here we will get the benefit that our decision statistic is just a linear function of the observations. Now, how do we compute the probability of error? Well, you know, we have two error events, and in our case here, they are symmetric, and the two hypotheses are equiprobable, so we can just focus on one of them. And this will be actually the average probability of error. So for example, you know, here, an error is basically if true hypothesis is H0. So if the true hypothesis is H0, basically the error is when you compute this quantity and it is greater than 0. Because if this quantity is greater than 0, you will make a decision in favor of H1. And that's an error because the true hypothesis is H0. And so what you can do is basically ask yourself, what is the probability that psi is positive, is greater than 0? Okay. Because this will make you decide in favor of H1, given, conditioned on the true hypothesis being H0. So this will be the probability of error. Now, to compute the probability of error, you need to compute, you need to obtain the distribution of psi. And in our case here, it's as simple as it can get. The reason is that we have a linear or an affine function of a Gaussian vector. And so you can show you have notes on Blackboard about jointly Gaussian random variables and Gaussian vectors. So there is a theorem that is proved there that an affine transformation of a Gaussian vector yields another Gaussian vector. Okay, and in our case here, you will get a Gaussian scalar. Okay, so what is nice, if you know that the distribution is Gaussian, knowing that the distribution of Gaussian, you need just to compute two things. You need to compute the mean, and in the scalar case, you need to compute the variance. Okay, so what is the mean of this thing under mu0 or h0, which is this hypothesis in which x has a mean of mu0? Well, what is the average of this thing? So you take the expectation. So the expectation of x under h0 is mu0. Okay, so it will be this thing. So you just put x equal mu0, and actually this thing can be written in a nice form, right? So again, you just plug in mu0, and well, this thing is the negative of the expansion of a square, right? So it's basically mu1 minus mu0 transpose R inverse mu1 minus mu0, and then with a minus sign, right? Because if you expand this thing, you will get minus mu1 transpose R inverse mu1, minus mu2 transpose R inverse mu2, and then the cross terms can be combined in this real valued case, and with a minus sign outside, it will give you 2 mu1 transpose R inverse mu0, okay? What about the variance? So the variance, it's a scalar. You take the variance is you subtract the first moment, you subtract the mean, and basically you compute the square of that, the expectation of the square. Okay, so you subtract the mean from here. This is a constant, so when you subtract the mean, this will be eliminated, and so we need to compute. So the variance of psi is the expectation of 2 mu1 minus mu0 transpose R inverse, x minus mu 0. So this is x minus its mean, and then you take the square. And then you take the square. But what is the second moment here? So the trick, if you don't know it, is simple. You know, yes, this is a scalar. This is a scalar. But you know, think of it as a vector. As a vector, you know, it can be written as, so you can think of this thing, it is exact, rather than multiplying it by another version of it, just a transpose. Okay, so again, the idea is, it's like you are taking the expectation of alpha transpose beta squared. Okay, so this is an inner product. So this is a vector, and this is a vector, and you are taking the inner product square. Well, what you can do is, and this is very useful in our course, what you can do is write alpha transpose beta, and then rather than squaring, or in the complex case taking the magnitude square, you can multiply by the transpose, and in the complex case by the Hermitian. So beta transpose alpha, because these two quantities are the same. Alpha transpose beta is beta transpose alpha. And so the trick here is to write down this thing as basically 2, it's 2, mu1 minus mu0 transpose R inverse x minus mu0, and then you multiply by the transpose of this thing, so there is an extra 2, and then you transpose this thing, so you have x minus mu0 transpose R inverse, and then mu1 minus mu0. So what is the benefit of doing something like this? Now you can apply the expectation. The expectation will be applied. So expectation, what are the random stuff here? It's basically this quantity. And what is the expectation of this quantity? It's expectation x minus mu0, x minus mu0 transpose. That's the definition of the covariance matrix of x under hypothesis H0. That's exactly equal to R. And so you have R sandwiched between two versions, R inverse and R inverse. So basically the product of the three guys will give you R inverse. And then once you know the mean value and you know the variance, you can just use the Q function to write down your probability of error. Okay, and later in this lecture, or if we are late, and you know, in the next lecture, I will give you the expression for the complex case, which is like sort of central to this course. I mean, you will not be able to solve any problem without basically knowing the correct expression. Okay, so here is the story of hypothesis testing. If your knowledge is rusty, it's very important, extremely important, and you need like to know MAP, ML. You need to know this idea that you do not just write down the rule. You need to simplify as possible, and you need to use your knowledge about probability and statistics. You need to know things like, oh, if I have a linear combination of jointly Gaussian random variables is Gaussian, and affine transformation of Gaussian vectors is Gaussian. And if we have Gaussian stuff, then we can focus on means and variances, or in the vector case on means and covariance matrices. Okay, and then there are tricks that are as simple as this. This one is very important. Okay, it's useful because again, it will allow you to write down something like this directly in terms. Once you have x minus mu0, x minus mu0 transpose, now you can just write down this thing as the covariance matrix of x, which is this. In this case, it's the same whether under H0 or H1. Okay, so this is a story. So please keep these things in mind. And our first topic today is level crossing rate. It's another parameter that often people who basically study wireless channels compute. And so what is the story here? So of course, we will stick to the flat fading model. Okay, so remember, what is the flat fading model? Flat fading model, it can be described in a number of ways. So one way is that the delay spread is much smaller than the symbol duration. Okay, so I remember the figure from the previous lecture. If the delay spread is much smaller than the symbol duration, then at the receiver you get shifted copies of the transmitted signal, but the shifts are small relative to the symbol duration, such that if you take a sample at a particular instant of time, your sample will depend on just one symbol. So basically your received signal will be something like, a channel gain factor multiplied by symbol. You don't have a summation or integration or something. Of course, g of t itself is an integral, but I don't have a summation or integration involving the symbols. Okay, so what if this is condition is not satisfied? What if the delay spread is actually greater than the symbol duration? Okay, if it's greater than the symbol duration, we don't have flat fading. And again, if you remember the figure from the previous time, now you take a sample at a certain instant of time, and you will find that the sample depends on a number of symbols. Okay, and basically, if the delay spread is much larger than the symbol duration, actually you will find that basically a sample taken from the received signal will depend on numerous symbols. Okay, so you have inter-symbol interference, and your signal will be basically dependent on a number of the transmitted symbols. Okay, so to have a flavor of this, if you have, so typically this is the stuff that you learn about in 242. And so there is a problem in homework 2, which you can find on Blackboard, in which you have the situation with inter-symbol interference, in which you find that the received signal is in fact it depends on a linear combination of two transmitted symbols. And in that case, if you have perfect knowledge of the channel, you go, the optimal receiver is something called the Viterbi equalizer. Okay. But the Viterbi equalizer, basically, it requires that you have, really good estimates of the channel, and with noisy channel estimates, its performance degrade significantly. Moreover, it is very computationally intensive. And so, basically in practice, people go for equalizer. So what is the word equalizer? If you have not basically heard it before, equalizer is basically a device that you use at the detector, or it can be an algorithm that you use at the detector so that you can handle the problem of inter-symbol interference, which is you have a received sample that depends on a number of symbols, and you want to know these symbols. What can you do? So basically the idea of equalization is it tries to sort of separate the symbols, okay, somehow. Again, if you have not studied this in 242, or if you have not taken 242 in the previous semester, it's not a problem. Basically, there are notes on Blackboard which you should read about for this week. You should read about the channel equalization, specifically the zero forcing and LMMSE equalizer. Okay, and then you will be able to solve a problem 4. Which gives you again a flavor of what will happen if we do not have flat fading. Okay, later in the course we will deal the problem with not having flat fading using OFDM. Okay, but for now it will be in the lectures flat fading model. Now basically the received signal model is a symbol times a channel. And let's have the channel now. Let's take its magnitude. So this is R of t is the magnitude of the channel gain, complex channel gain. And it's something that it changes over time due to mobility. Mobility of the transmitter, of the receiver, of the scatterers in the environment. So you will basically, if you go and plot the magnitude of the channel gain as a function of time, sometimes it's high, sometimes it's low. And level crossing rate, it means that you specify a certain level, let's say gamma, and then you ask yourself, on average, how many times R of t goes below gamma. Okay, so this is specifically, this is the downward level crossing rate. Okay, so this is the number of instants per unit time, let's say per second, at which R of t, so basically the events we are interested in are those blue dots, because at those events, R of t goes below, so it's higher than gamma and then it's lower than gamma. So we want to know basically the average number of these per unit time, and that's called the downward level crossing rate. You can study the upward level crossing rate. I will leave this as a homework problem in homework 3. The upward is basically when you go above a certain level, and you can study the overall level crossing rate, which is you basically pass through a certain value, and you don't care whether you are going below it or you are going above it. And the overall level crossing rate is just the sum of the downward level crossing rate and the upward level crossing rate. In this lecture, our focus will just be the downward level crossing. Okay. Now, you need assumptions. As usual, from the very beginning of this course, we are making like lots of assumptions. So of course, like to study, the level crossing rate of a random process, you need it to be sort of nice, well-behaved. And so we'll assume that the process actually has a mean square derivative and that it is ergodic. Okay, so ergodicity is a notion that is stronger than stationarity. And like basically the ad hoc definition of ergodicity is that we can infer statistical properties from one sample of the random process. Okay, so you have one sample of the random process and you can use it. Okay, so here one sample means that basically it goes to infinity. So you have basically you have one realization of the random process that extends over the whole time. So in practice, it should extend over a huge period of time. But just one realization, and you can make, basically, you can estimate the statistical properties. So these can be the mean, the covariance, and so on. Okay, so in this course, we will just mention ergodic like superficially. We will not basically go deep into it or anything. It is in 241 if you have taken it or you are currently taking it in this semester. Okay, but so for me, I will not go into details. It's just not, it's a strong form of stationarity again, in which you can infer something like the mean of the random process by just observing a realization from one sample. The sample is called the realization. Okay, and I will give you an example, how this can be applied. Okay, suppose that you have an interval. So this is t plus delta t, and delta t is infinitesimal, so it is very close to t, and it is small enough, and our process is nice, such that if there is a crossing, on the interval from t to t plus delta t, it is just one crossing. Okay, so basically here is our level, which is gamma, and if there is a crossing here, then r of t will do something like, it will come like this, and it will go below the level gamma. So this is r of t, which is the magnitude of the complex channel gain. So here we have a crossing, and again we assume that delta t is small enough such that the probability, basically, this process may go up and then go down again, but we will assume that delta t is small enough and that our process is not changing too quickly, so that on basically a very small period of time, the probability of having more than one downward crossing is negligible. Okay, so you can have a crossing, or perhaps t plus delta t, so this is level gamma. Perhaps you don't have a crossing. Perhaps r of t is doing something, is doing something like this. Actually, here it is increasing, right? So here we have a crossing, and here we don't have a crossing. So here we cross the level gamma. And so let's define a random variable z. And so z is 1 if there is a downward crossing, and it is 0 otherwise. So z is a Bernoulli random variable. Okay, so z is Bernoulli. It's a 0, 1 random variable, and it tells you, so if it's 1, it tells you that on this interval you have a crossing, a downward crossing, otherwise you don't. So this is the official definition of the downward level crossing rate. So we have the expected value of z. Because z is Bernoulli, then this is actually the probability that z is equal to 1. So it is the probability that you have a crossing, okay, and you scale it, you divide it by delta t, and take the limit as delta t goes to 0. How can we compute something like this? Okay, so what is the probability that z is equal to 1? Okay? And I am conditioning here, so to be clear, let's actually add this conditioning. So the trick here is to condition first on the value of the first derivative, which is the mean square derivative in our case. Okay, because so what is the probability that you have a downward crossing? Well, you have a downward crossing if, so our interval is t and t plus delta t. So when do you have a downward crossing here? You go below gamma. So if at the beginning of the interval you start higher than gamma, and at the end of the interval you are below gamma, okay, then that's a crossing. Okay, and again, delta t is a small enough, because you can say, well, you can start above gamma, go below gamma, go above gamma, go below gamma, and so on, numerous times. Okay, well, yeah, that's true. That's true if delta t is large enough. Okay, so from the very beginning, remember, that's, the idea that the definition here, it has the limit as delta t goes to 0. So we are interested in, extremely small values of delta t. So once we have those values, the probability of events like, going, several crossings will be negligible. And this will be our main event here. That basically to cross the level gamma, you need r of t to be greater than gamma. Okay, so here is t. So at t you are above gamma. So this is t plus delta t. At t plus delta t you are below gamma. Okay, so this is basically our process is doing something like this. And so there is a crossing. There is a crossing, a downward crossing. You may say, okay, so what is this business of the first derivative? I mean, these two guys are just written in terms of r of t. So the second order of business is to use Taylor approximation. Okay, so Taylor approximation, it tells you if delta t is small enough and our function is nice, okay, then basically r of t plus delta t is approximately r of t plus the first derivative multiplied by delta t. Okay, so to have equality here, you should evaluate the first derivative at a time instant between t and t plus delta t, but this will make things complicated. So again, here we will just go for an approximation and not an equality. Okay, assuming again that r of t is nice enough and delta t is really, really small. Okay, so this is why the first derivative will enter into the picture, and the first derivative is another random process, right? And so here we have the process itself and its mean square derivative. That's a lot. And so let's just think of the first derivative as if it's like fixed. Initially we will just initially we'll just fix it. Okay. rewrite the inequalities. Okay, so to have a crossing, R of t should be greater than gamma. R of t should be above the threshold. R of t plus delta t should be below the threshold, and so R should be R of t plus delta t should be less than gamma. And now we will use the Taylor approximation. So this means that R is less than gamma minus the first derivative multiplied by delta t. And you will note here that I dropped the time dependence t. Where is t here? I dropped it under the assumption that actually my analysis will not depend on t. So that's the reason that I assume the stationarity. So stationarity means that, well, I mean, the distributions that are needed for this problem do not really depend on time. Okay, so you can just think of R of t as R, and R, dot, or the first derivative of R with respect to t, which I mean is in the mean square sense. You can just work with them without explicitly mentioning t, because regardless of t, the distributions will be the same. Okay, so what is this probability given the first derivative? What is this probability given the first derivative? First, note the following, that if the first derivative is positive, or actually it's zero, you will never do this crossing, right? So suppose that you start here. So again, this is t plus delta t, and suppose that this is the level gamma, and you start here above gamma. Now, if your derivative is positive, you are increasing. If it's zero, then you are constant. You will never cross. Okay, so the probability of this event that R is greater than gamma and less than gamma minus R, the first derivative delta t, you need actually this guy to be negative, okay, for this inequality to make sense. Okay, and so here is an indicator that the first derivative is negative, so that you do a downward crossing. And then you say, okay, to compute the probability, if I give you a random variable, so this is R of t, so you have a random process R of t. If you fix t, you will get a random variable with a certain distribution, and again under the assumption of stationarity, this distribution does not really depend on t. Okay, so what we will do is say, okay, this is a random variable, and here we are fixing the first derivative. So basically, this probability is the integral of the conditional probability of R given its mean square derivative at the value t. So this is again f of R of t given R1 of t. I mean, if it makes you happy, you can write it like this. But again, under stationarity, basically this distribution will not depend on t. So you take this PDF and you integrate it from this guy to this guy, gamma to gamma minus the first derivative multiplied by delta t. Okay, so you have a probability random variable living between two values here. And again, don't forget that this guy itself is a random variable. Okay, and so fixing it, this becomes a constant, but now we need to use not the distribution of R, but the conditional distribution of R given R dot, or basically the first derivative. More approximations. Delta t is very, very, very small, right? So if you are integrating a function, let's say psi of alpha, from alpha 0, the alpha 0 to alpha 0 plus epsilon, and epsilon is very, very small. So as an approximation, again, for nice function, this is basically, it's like psi of alpha 0 multiplied by epsilon. Right? Because if the interval is very small, you can just assume that the function is like sort of almost constant. Take it outside and then multiply the value of the function by epsilon. So we'll do the same here. So this is approximately, and so we will evaluate the conditional distribution at gamma, and then multiply by the length of the domain of integration, so this minus that, which gives you this value. Okay, so this is the conditional. This is the conditionals. Okay, Again, so this is the conditional probability that you have a downward crossing given the first derivative. But the first derivative itself is a random variable, so the probability that z is equal to 1, so this is the unconditional probability, which is needed in the definition. So the definition is you take this probability, divide by delta t, take the limit as delta t goes to 0, and so basically this probability, what you do is you take the conditional, you multiply by the PDF of the mean square derivative, and then you integrate. Okay, and so we can take the conditional probability, put it here, and because we have this indicator that the first derivative is negative, then actually our integration is from minus infinity to 0. And you can combine basically the PDF of R given its mean square derivative multiplied by the PDF of the mean square derivative. You can just combine them and write them as the joint distribution of basically R of t and R1 of t. Okay, so we need this, okay, of R of t and R1 of t, which here again will not depend on t under our assumption. Nice, because now you can just, if you divide probability z equals 1 by delta t, you get something that is basically not a function of delta t. So you take the limit as delta t goes to 0, and this will be, so this integral here is the downward level crossing rate. So it is an integral. It is an integral. You can write it like this. Okay, so let me write it in another way. It is the integral from minus infinity to 0 of, you can call this any dummy variable of integration. So this is u, and this is the joint distribution. So let's write it here. So joint over, it's of R of t, R1 of t, of gamma u du. Okay, so to compute something like the LCR, you need the joint distribution of a random process and its mean square derivative. Okay, so it's needed. It is needed, like, to do this type of analysis. And so you will do something like this. Of course, like the simplest process for which you can compute such joint distribution is a Gaussian process. So basically we will do it in homework 2. The current homework, you can say that problems, it's the fifth problem in homework 2, and it's along with problem 4, they are like very important. So in problem 5, you will basically compute something like this. You will like sort of start from a Gaussian random process, and you will proceed step by step to obtain the basically the relation between R of t and its derivative. Remember that R of t itself is the absolute value of g of t. Okay, so you start with a distribution for this g of t, which I think in the problem is called big X of t, and you know, the problem will basically take you step by step, basically in 2 or 3 steps. You basically reach a nice formula for basically the joint distribution that is needed to compute something like the level crossing rate. Okay. Now, another parameter is the average phase duration. So average phase duration is, okay, so suppose that you go below gamma. So you go below gamma, you stay for a while, and then you go upward again. I mean, it's, you know, it keeps fluctuating over time because of mobility and so on. And so here you go below gamma and stay for a duration t1, and then you go below gamma and stay for a duration t2 before rising above gamma again, and so on. And so we are interested in, you know, something called the average phase duration, which is the average of those guys. Okay, AFD. So how can we obtain a formula for the average phase duration? Now, what is the probability that R is less than gamma? Again, it's R of t, but under stationarity, it's just R. What is the probability that R of t, which is the magnitude of g of t, is less than gamma? you know, if you know the distribution of R, just integrate the distribution from 0 to gamma, and you will get the probability that R is less than gamma. But we can obtain this probability using this, and here is a use for ergodicity. So, basically the idea with this is to do something like this. You say, okay, suppose that I have one realization of a random process that is long enough. I have one realization that is long enough. Then the probability that, basically R goes below gamma, is below gamma in value, it can be obtained from the realization itself, from this particular realization, if the process is indeed ergodic. What you will do is you will measure, so you keep measuring the process, and you measure those T1, T2, T3, T4, and so on over a huge observational period. And then what you do is that you sum the T's and divide by big T. And, again, you need T to be really big. So here we have limit as T goes to infinity. So basically, this equality here is one use of ergodicity, in which, like you say, well, I can infer at least some of the statistical properties of the random process by observing a long enough realization. Okay, and now, what is this, with this summation? So I will multiply and divide by n of big T, and big N of big T is the number of times R of T goes below big gamma. Okay, so you start with this summation over big T, which is the period of observation. And so here I didn't put an arrow because it should be too long. Okay, theoretically speaking, it should go to infinity. And big N of T again, so I multiply and divide by big N of T, and let's see. So what is this thing? Okay, so we have a limit of a product. Let's assume that the limit of each term is finite. Okay, and is a finite positive number. What is the limit of N of T over T? So what is N of big T? It is a counter of the number of times that you go below a certain threshold. So if you count the number of times, you go below a threshold, and you divide by the observation time, and suppose that the observation time is long enough, then this is like, it's the number of downward crossings per unit time, right? So you compute the number of downward crossings over a duration big T, you divide by big T and take the limit. Okay, again, there is this implicit assumption of ergodicity. Actually, it's explicit, I said it here. This assumption of ergodicity, which tells you that, yes, if you want to compute, like experimentally or empirically obtain the level crossing rate, you can do something like this. If the process is indeed ergodic, basically go and obtain one realization from the process, count how many times the process will go below a level, divide by the time duration of your experiment, and this will give you a good estimate of the level crossing rate, the number of downward crossings per unit time. Okay, so this will go to the LCR. What about this limit here? It's the average phase duration, right? It's the sum of those T's, the sum of those intervals during which the process is below gamma. So you sum them, and then you divide by their number. Okay, and so this is the so-called, by definition, the average phase duration. So this thing will be the level crossing rate, and this thing, by definition, will be the average phase duration. And so the average phase duration is the probability divided by, you move this to the other side, divided by the downward LCR. Okay, so to obtain the average phase duration, you need, okay, so let's write this thing. So in the numerator, you need this probability, and so you need the PDF of R of T. right? So that you compute this guy. In the denominator, it's more complicated. You need basically the joint PDF of R and R1. Okay. Okay, so you need these guys so that you can compute something like the average phase duration. The idea of writing down expressions for statistical properties from one realization that is long enough, again, it is not a, it is not like something that I you may think that you may go to extremes, like thinking that it's never impossible, or thinking that actually for any process we can do so, but it's not true. And again, for those of you who took 241, I am sure that you studied conditions on, for example, when the process is mean ergodic. So what is a condition so that you can estimate the mean of a random process just by looking at one realization? There is a condition. If you want to estimate also the covariance, then there is a condition, and so on and so forth. Okay. Again, we will not delve into details here. I will, we'll just take the definitions, and we will focus on like basically how to compute those guys. Okay, so and computing them again will the biggest obstacle is actually this one here, the joint, and so you will do exercise 5 to basically do this. Of course, needless to say, please start as early as possible. Please do not procrastinate. Okay, and ask me via email. Attend the office hours. Okay. Any questions? Is anyone awake? You're awake, right? No?
Yes.
Yes, sure.
Okay. Yeah. Okay. So 2 are awake. Great. So MIMO channels. Modern communication systems can achieve a high rate using multiple antennas at the transmitter and receiver. Okay, so MIMO is a word that it's a word that is used in system theory in general, and it means multiple input, multiple output, which means that we are talking about a system with multiple inputs and multiple outputs, nothing else. In the context of wireless communications, multiple inputs means that you basically generate propagating signals in the wireless medium via multiple transmitting antennas, and you basically deploy a number of receivers to pick up those electromagnetic waves and get from them some useful information for the receiver. So multiple antennas. So basically in communications, inputs and multiple inputs and multiple outputs will be multiple antennas on the transmit side and multiple antennas on the receive side. So definitely MIMO is a very important part of this course. Modern communication systems are basically MIMO of DM. Okay, so combining these two ideas together, MIMO and OFDM, gives you basically, the current modern systems, Wi-Fi, LTE, new radio, all these standards, they basically rely on MIMO OFDM. Okay, so basically this is, things are now like sort of boring. I mean, the wireless modeling is not, is at least to me, of course, I mean, some people, it's, their research and their basically speciality is wireless modeling, and definitely it is nice to them. And I have known people like basically doing, measurements, walking around with network analyzers connected to horn antennas and stuff like this. But here we will focus like sort of, once we finish this part, we will start doing the performance analysis and how to actually understand those systems. But the first part of this course is needed because there will be terms that I will use later, and we need actually to agree upon ourselves, among ourselves about like things. What is the what is the coherence bandwidth? What is the coherence time? Stuff like this. Okay. For the MIMO channel, again, you have antenna arrays. You have multiple antennas, and so how do you configure your antennas? You can put them on a circle, or you can put them along the line. You can put them in some fanciful configuration. So, for the purpose of this lecture and this course, we will just focus on uniform linear arrays. So linear, so you deploy your antennas by putting them along the line. Okay, so this is the transmit side. Those are our antennas, and they exist on a line. Okay, so that's the reason we call the array a linear array. Uniform means that you don't just put them on a line. The distance between two neighbors is the same. Okay, so the separation, the distance between antenna 0 and antenna 1 is dt, the distance between antenna 1 and antenna 2 is dt, and so on and so forth. So they are uniformly spaced. Okay, can you make the spacing different? Yes. Can you deploy the antennas basically in basically rectangle, in two-dimensional array or something like this? Yes. Okay, so all these are possibilities, but again, conceptually, this will be enough. Think of the antennas as arranged along a line, and they are uniformly spaced. So this is the transmit array. Okay, and so it is basically, so the space, there is an origin for the space, and the position vector of antenna 0 is this xt. Okay, so this is a vector connecting the origin of your coordinate system to antenna 0, and then et hat is a unit vector along basically the direction of the array, right? So those guys are arranged along a line. So this line has a direction, and so basically vector et is a unit vector in that direction. Okay, and suppose that we have nt transmit antennas, and so our antennas are numbered 0, 1, 2 up to nt minus 1. Okay, the receive array will be the same. So the receive array, there will be antenna 0, antenna 1, antenna 2 up to antenna nr minus 1. If we have nr antennas, you can connect the origin of the coordinate system to this antenna here. So this will be xr, and then those guys are on a line, and so this line, the unit vector in the direction of that line is er, like this, and the separation between two antennas is dr. So like the transmit array, basically the receive array will be characterized by those 4 parameters, right? So you need the number of antennas, nt on the transmit side, nr on the receive side. You need a unit vector telling you, so those antennas are arranged along the line. So what's the unit vector in the direction of that line? So these are et and er. Then you need like the position vector of antenna 0 on both sides, xt and xr, and then you need the separation. Okay, and you need just one parameter for the separation because the arrays are uniformly spaced. Okay, let's focus on the channel connecting the nth receive antenna and the nth transmit antenna through a scatterer at x. Okay, so so here is antenna. So this is the nth transmit antenna. Okay, and then signals will come out, and then you go to a scatterer. So there is a scatterer here. Okay, it has a certain position vector, which is big X, and then part of the scattered signal will go to the nth receive antenna. Okay, so we want to study this thing. So the signal will go from the transmit antenna again, but the antenna will basically radiate the signal in, perhaps if it's omnidirectional, over the whole upper hemisphere, and then part of the signal will go and hit the scatterer, and then part of the scattered signal will go to in the direction of the nth received antenna, like this. Okay, so what is this, a channel? Okay, so you need assumptions. We typically assume that the antennas are far apart from one another. and that the scatterer is far apart from both antenna arrays. And then basically, when you talk about the propagating wave, so if you haven't studied any like course on wave propagation, but like typically, propagating waves, they have phase factors that look like this: e to the I 2 pi over the wavelength, and then sort of a distance. Okay, so we'll measure distances, and so it is useful actually to have an approximation that makes our life easier. Okay, so this is the approximation. So suppose that you add two vectors. Okay, here I am putting this arrow here, just to emphasize that the vectors I'm talking about in this problem is like actual vectors. Okay, so like they are vectors in the real space, connecting the origin to some antenna, stuff like this. Okay, so so typically like vectors, I just write them with and you know from the context that they are vectors from their dimensions and so on. But here I'm putting this arrow like to say, oh, we are actually talking here about vectors that you can imagine. They are geometric vectors. Okay, so if you have a vector plus another vector, and it happens that the L2 norm of this vector, its Euclidean length, is much smaller than this vector, then the L2 norm of the sum of the two vectors is approximately the L2 norm of the big guy plus a dot product or inner product, a dot product between a unit vector in the direction of the big guy plus, and the smaller guy. Okay, so again, the idea is that if you have a vector and another vector, you are interested in this L2 norm. This is basically, we have the L2 norm of y is much greater than the L2 norm of epsilon. Then this is approximately the L2 norm of the big guy plus you take a unit vector in the direction of the big guy. Okay, a unit vector in the direction of the big guy, which here I called u, and then you have the dot product with the small guy. Okay, so this approximation, again, as we'll see, it will make our lives easier. And to see this, I mean, quickly, you can just write down things explicitly. The L2 norm, you basically you sum two vectors, you add the components, and you square them, and then you take the sum, and then you take the square root, expand the squares, and when you expand the squares, you will get here the L2 norm squared of vector y and the L2 norm squared of vector epsilon. This is negligible, right, by assumption, and so you are left with basically these two terms. Pick up this as a common factor, and this will be the L2 norm of vector y, and what you are left with is basically this square root 1 plus 2 multiplied by the sum divided by the sum of yi squared. Then square root 1 plus something that is very small can be approximated by 1 plus basically double, 1 plus half, basically this is a small thing. So square root 1 plus alpha for sufficiently small alpha is to, is very close to 1 plus alpha over 2. Okay, and so what we can do is that square root is like very annoying to have in our expressions, and so we can just say, okay, is the square root of this thing 1 plus 2 something is just 1 plus the thing itself, so divide by 2. Okay, and then distribute back the L2 norm of y, and so it will give you basically our result here, that the L2 norm of the sum is the L2 norm of the big guy plus a unit vector in the direction of the big guy dot the basically the small guy. Okay, any questions? Okay, so that's our geometry, and again we will take it for granted that whenever the a signal propagates under some assumptions, basically it gets this factor e to the I 2 pi over lambda, and then the length of the path. Okay, now to write down something like this, actually, let me state explicitly one of the assumptions. You need to assume, that makes actually this valid. You need to assume that the time. So you have an array, right? So suppose that you have an array like this, and then there is a coming wave to the array. So here the wave will hit this antenna first before reaching this antenna, right? Because the wave propagates with a huge but still finite speed. So there is a delay between the signals received in the various antennas, right? So the wave comes and it does not really reach all antennas at the same time. So there will be delays. So if those delays are much smaller than the symbol duration, then we say that our array is operating in narrow band. Okay, so narrow band, I mean, very annoying. It's like the third use. So narrow band in the first lecture was the bandwidth of the signal is much smaller than the carrier frequency. Narrow band in the second lecture was the bandwidth of the signal is much smaller than the coherence frequency or the coherence bandwidth of the channel. Now, narrow band in the context of arrays is this assumption that the symbol duration is much greater than the basically the delays, basically delays encountered in the array itself. Again, because the wave front will not reach each antenna at the same time. Okay, but for our purposes, I mean, you can just hear this, and it will not like make any significant difference. We will just stick to this model. My point is that don't just consider that this is like sort of universal. Okay, everything here written, it's predicated on perhaps an array, a full array of assumptions. Okay, so do not just take it and use it under any situation, because it may not be valid. Okay, for our purposes here again, we will again assume that the signal it takes this phase factor, and so it now becomes a matter of distances. So this is the nth element in the transmit array. This is the nth element in the receive array, and we are studying basically a signal going from the nth element to the nth element through this scatterer here. So the signal travels this, so it goes to this scatterer, and then from this scatterer to basically the receive array, and the signal will get a phase factor which is equal to e to the I2 pi over lambda multiplied by the length of the path, which is the sum of two vectors. So we are talking now about the length of the green vector and the length of the orange vector. Length of the green vector and the orange vector. Okay? So what is the green vector? What is the green vector? It's basically this vector here between these 2 points. The vector between these 2 points is the position vector of the endpoint, which is x, minus the position vector of the nth transmit antenna. So what is the position vector of the nth transmit antenna? The position vector of antenna 0 is x sub big T, and so basically the position vector of the nth antenna, so you go from the origin to antenna 0, so that's x of t, and then you travel a distance m dt along the direction of the antenna array, which is basically characterized by the unit vector et. So you start with x from the origin to antenna 0, and then you go a distance mt in the direction of et. The difference between these two vectors is simply the green vector. Okay, so this difference is the green vector. And the orange vector will be this difference here, again using similar reasoning. So the L2 norm, again, the L2 norm is annoying because the L2 norm of a vector, like you square the components, then you sum, then you take the square root. Okay, so we don't want like those square roots and so on, so we will just apply our approximation. So we will take this vector, so we have this x minus xt minus m dt et. So this is the big guy. We'll assume this is a big vector. it has a large L2 norm compared with this small vector. Okay, and so we can apply our approximation, which tells you that the L2 norm can be written as the L2 norm of the big guy plus you take a unit vector in the direction of the big guy, so a unit vector in this direction, so it will be the vector x minus xt divided by its L2 norm, and then dot basically this, which is the small guy, mdt et. And you will do the same for the second vector. So you get this thing here. Okay, and here you don't find any dependence on you don't find dependence on n and m, and typically this phase factor is considered as a part of the channel gain. Remember, in the first lecture I did something like this. So there was a gain factor, and every time we do like a Fourier transform or inverse Fourier transform, we get like a phase factor that is like sort of irrelevant. So we just say, okay, combine this thing with the gain factor of the path, and so we'll do the same here. And actually, this will be our hero. So this term here is what is important. Okay, so so to characterize the propagation from the nth antenna in the transmitter array to the nth antenna in the receiver array, we have e to the I 2 pi over lambda, and then we have ndr, and then ur dot er minus mdt ut minus et. Okay, and so very important to keep in mind what are those things. Let's talk about one of them, and then the other is by analogy. So what is ET? ET is a unit vector in the direction of the transmitter array. Okay, so this is the transmitter array. This is a unit vector in the direction, again, of the transmitter array. What is UT? UT, it's the vector here, basically from xt. So basically it is a vector that gives you the direction, so it's unit vector in the direction of the scatterer. Okay, so what is u of t? It is x minus xt, x minus xt, normalized, of course. So x minus xt, again, you are basically getting a vector connecting specifically antenna 0 to the scatterer. Okay. So the dot product between these two guys, remember what is the dot product? So et dot ut, the dot product of two vectors is the L2 norm of the first, which is 1, the L times the L2 norm of the second, which is 1, times cosine the angle between them. So it's like cosine this angle. So if this angle is is 8, it's like cosine 8. So this is a parameter that tells you again like the direction between the line of the antenna array and basically the direction to some scatter. Here we are considering just one scatter, and shortly we will talk about like what if you have more than one. Okay, now this is between the nth antenna and nth antenna. And if you look at this quantity, so basically this expression is for, you can choose n. So this is for n from 0, 1 to nr minus 1, and m is from 0, 1 to nt minus 1. Okay, and so we can, since once you have something with two indices like this, it is very tempting to basically connect those terms in a matrix, right? So if you have something with two indices, it sort of makes sense like to just think of this quantity here as an element of a matrix that you have a row index n and a column index m, or vice versa. Okay, so this is what we will do here to obtain those phase factors for every n and m. So for every antenna on the transmit side and every antenna on the receive side, we will define two very important vectors, vector A and vector B. So basically, I will call this dot product omega sub r, and I will call this dot product omega sub t, and then vector A is basically e to the I 2 pi over lambda, okay, and then you have an integer multiplied by dr omega r, and this integer is 0 or 1 or 2 up to nr minus 1. Vector B is parameterized by omega t, which is the dot product of ut et. Okay, so this is, again, it's cosine. You can think of this as cosine the angle between the receive array and basically the direction coming from the scatterer at position vector big X. And this vector again is e to the I 2 pi over lambda, and then you have an integer going from, going through the values 0, 1, 2 up to nt minus 1 dt and then omega t. So these are the two vectors. And now you get those phase factors by basically writing down the outer product of these two vectors, right? So you take A, vector A, and you multiply it by the Hermitian of vector B, and so you get a matrix. So this is a matrix of dimension nr by nt, right? And you can check this here. What if you take this vector? Actually, let's do it. I mean, it's not bad to like. So this is our vector, e to the I 2 pi over lambda 0 dr omega r, e to the I 2 pi over lambda 1 dr omega r, and then the rest. So this is vector A. Vector B, you basically take its Hermitian, and so it is converted to a row vector, and then you take the complex conjugate, and so this will be e to the minus I 2 pi over lambda 0 dt omega t, e to the minus I 2 pi over lambda 1 dt omega t, and e to the minus I 2 pi lambda 2 dt omega t, and then you multiply. So this is going on. So when you multiply, you get basically a matrix. So the first element will be 1. The second element will be e to the minus I 2 pi over lambda 1 dt omega t. Okay, because this guy is 0, and the second element here will, let's actually write it with a 0. It's okay. It's just an index for the antenna, minus I 2 pi over lambda dt omega t, and this one will be e to the I 2 pi over lambda 0 dr omega r, and then minus 2 pi over lambda 2 dt omega t, right? So basically, if you take the nth, and here we are numbering from 0, and you take the nth one, you will basically get this vector here. So now say hello to basically this thing. It's called the channel matrix. So whenever we have MIMO system in which we have multiple transmitters and multiple receivers, think about it. It's like you are actually talking about NR times NT channels, because you have a channel between each transmitter and each receiver. Like, so if you have two transmitters and two receivers, two transmitters, two receivers, two transmitters, two receivers, then you have how many channels? This one, from antenna 0 to antenna 0, from antenna 0 to antenna 1, from antenna 1 to antenna 0, and from antenna 1 to antenna 1. You have 4 channels. So this is something, regarding, I mean, you see, so there are, details, not justified and so on, but this is very crucial, that once you start talking about multiple antennas, and it will come later in this course, we talk about not just a channel as a scalar, but we talk about a matrix. Because once you have an array on the transmit side and array on the receive side, if this one has NR, if those have NR and NT antennas, then actually the number of channels we are talking about are NR times NT. And we typically think of a channel matrix. Okay, so basically, if you have an element, N and M, basically it tells you something about, basically the relation or the channel between the nth receive antenna and the nth transmit antenna. Okay, so channel matrices will come, they will come later to us, and they will play an important role in analyzing things like MIMO systems, and also actually in OFDM. So matrices will also appear in OFDM, but for a different reason that, it's not time to talk about it now. Okay, so any question?
Yes, Professor.
Yeah. Yeah, I hear
what
you.
is what is the role of the narrowband assumption in this derivation?
Without it, this is not true. We say that the received signal is some factor that, so here I am saying something that basically the received signal is, there will be some amplitude factor, and it will be proportional to this guy. This is an assumption. Okay, so you can show that basically if you remember what we did in the first lecture, like you have things like as a function of time and so on. If you do things very rigorously from very first principles, you will discover that the received signals at the different antennas cannot be written as such, unless you make this assumption. Okay, so as this assumption makes this valid. Okay, so this is, let's actually write it explicitly, valid under the narrowband assumption. Okay?
Okay.
And this expression, again, after using our assumption regarding the L2 norm of a big vector plus a small vector, will end up like having this nice form. In many cases, actually will go for this, but if you study like a wideband array, then you need to be careful. Most likely the expressions here will not be suitable.
And another quick question: those vectors,
yes.
A omega r and A omega t, are what are called steering vectors?
Yes, they are. Yeah, yes, that's true. That's true. Yeah, in the context of antenna arrays, typically those are called steering vectors, and they are basically those vectors like with those progressive phase shifts. Basically with something related to the direction, right? So yeah, yes. See, if you want to go on, Steve. So means steering vectors, antenna response vectors, or array response vectors. Okay, so yeah, they appear in the literature with several names. Okay.
Okay, thank you.
Yeah. Okay. In antenna arrays, just an additional comment. In antenna arrays, like people also talk about something more sophisticated than what I'm talking about, which is the ability actually to add a phase shift to the received signal. So you can manipulate basically the array. We will do something very similar to this when we study the topic of beamforming. Okay, so vectors, not exactly, but similar to what I am showing here. Sometimes they are called precoding, beamforming vector. Again, like just wait. I mean, we do not. I do not want to get ahead of myself. Okay. So now, if the channel matrix can be written as an outer product of two vectors, what is its rank? Okay, so if I can write H as A, B, Hermitian. Okay, so it's a column vector multiplied by a row vector, right? So basically, this is of dimension nr by 1. This is 1 by nt. So the rank of H is 1. Okay, the rank of H is 1. You have one scatterer, the rank is 1. Well, I mean, who cares? I mean, what is the issue here? Again, it turns out that the channel matrix, the rank of the channel matrix is very important. Okay, so you may think that it's like a mathematical concept. Who cares? it turns out that it actually has physical implications. So we'll see this later. If you have an antenna array, okay, you can use it to transmit a number of data streams simultaneously. So basically, this is how antenna arrays can achieve a high rate of transmission. You can transmit high symbols by basically bumping into the air multiple independent symbols simultaneously. It turns out that to do this, you know, the number of streams you can transmit simultaneously depends on the rank of the channel matrix. Okay, so you cannot exceed the rank of the channel matrix. So the fact that you have NT transmitters does not mean that you can transmit NT streams simultaneously, right? So you can have this idea. If I have NT transmitters, why not just transmit a packet of data from the first antenna, a different packet from the second antenna, a third packet from the third antenna, and so on? And those packets are different, right? It turns out this is not true at all. Okay, so basically the number of streams you can transmit, you know, is not just NT. It is related more to the rank of this matrix H. So if the rank is 1, that's it for you. You know, basically you can just transmit one stream and decode it reliably at the receive side. So again, we will see later that the rank of matrix H is really important. The rank is 1 if you just have one scatterer. What if you have 2 scatterers? Okay, so this is the transmit array, and this is the receiver array. Okay, and let's suppose that there is one scatterer here, so you go to the scatterer. So this is 1, and there is another scatterer. Okay, so basically, let's say that it's here. Of course, you know, this, my drawing here is ridiculous because actually the assumption is that, you know, those arrays are very far apart and the scatterers are very far from both. So you know, so again, don't take this this figure literally. It is not true. If things are very far, to basically justify the you know, the assumptions in the derivation. But in the case that you have multiple scatterers, and under the assumption I mentioned during the first lecture, we basically take the wireless channel to be a linear system, so you can apply the principle of superposition. So you can say, well, if we have 2 scatterers, then, okay, then you take the, you know, the outer product corresponding to the first scatterer multiplied by the respective gain factor. You take the outer product corresponding to the second scatterer multiplied by the respective gain factor or amplitude factor, then you just sum them together. What if you have 3 scatterers? You know, well, I mean, you can just write a you know, this general formula for L scatterers. Okay, so you can just write down this. Now, what will be the rank? What will be the rank? In the next lecture, I will focus on the what if you have 2 scatterers, okay? Because if you have 2 scatterers, well, now the dimensions are, you can write down matrix H as NR by 2, a matrix that is 2 by 2, and a matrix that is 2 by NT. So what is the rank? The rank can be 2 now. So the rank can be equal to 2, but it can also be equal to 1. Okay, so if you have 1 scatterer, I mean, this is rank 1. It's a rank 1 matrix. No way. If you have 2 scatterers, you have the possibility of raising the rank to 2. But is it guaranteed? if you have 3 scatterers, you can raise the rank to 3. But is it guaranteed? Okay, so we need to understand this, this part. Okay, because this is very important. If you you need to have like an understanding of what does it take for MIMO to work. Just deploying multiple antennas is not enough. You may deploy multiple antennas and you can have many scatterers, and yet you get a rank 1 channel over which you transmit more than one stream of data at the same time.